Hello everybody. In this lecture we're going to look a little bit more depth at Hodgkin-Huxley voltage-gated ion channels and the outcomes of their activity. So just to remind you, the voltage-gated ion channels are just the same formulation as before. They are variable resistances, each in series with its own voltage, and you can have a large number of them, and typically do have a large number of them in each cell, in each compartment, and the compartmental equivalent circuit is much the same as you have seen it earlier, with the capacitance, membrane resistance, axial resistance, and resting membrane potential. To remind you, these are the heroes of this lecture and the previous one and coming one as well, Hodgkin and Huxley, who did the beautiful experiments and made the absolutely spectacularly prescient model to describe the behavior of these channels. They described, among other things, using their derivation for the properties of the potassium and sodium channels, they described how you could get an action potential. Many years later, we now have an idea of the structure of these channels. These have 4 domains, each with multiple loops going through the membrane, and the combined action of these allows ions to go through the inner pore when there is the appropriate voltage change. The formulation that Hodgkin and Huxley came up with was that the actual conductance at any instance is equal to the maximal conductance due to that channel times some powers of this fraction term m and h, which refers to the fraction of the channel gates in the open state. And the way these channels open and close is in a voltage dependent manner. If you think of it like a chemical reaction, it goes from the closed state with a forward rate of alpha to the open state, and it goes back from the open state with a rate of beta back into the closed state. And if m is the fraction open, then 1 minus m is the fraction closed, and of course m is the fraction open. And the key thing is that these alpha and beta terms are functions of voltage or membrane potential, and they're also equivalent. They can be mathematically related to the steady state value of m, which is m infinity, and tau, which is the time it takes to reach this steady state value. And so these put together give you all of the dynamics that Hodgkin and Huxley derived for the voltage-gated ion channels. Just to give you a glimpse of the kinds of complexity that you get out of this, which we'll be seeing in the coming lectures. This is a model of a Purkinje neuron. This is based on work that Eric de Schutter has done. These are beautiful images from his work. And here's the soma of the Purkinje neuron, and here's the beautiful branching dendritic structure. And the colors indicate the membrane potential. And you suddenly start to see that the cell is not at all one homogeneous domain. The ion channels cause different regions of the cell to be at very, very different potentials. Some of these ion channels are ligand-gated channels, which we've already seen, and some of them are voltage-gated ion channels. So you can have action potentials initiated up here. You can have propagating action potentials back and forth from the soma. A lot of very interesting dynamics, and we'll get to see much more of this. The lower panels refer to calcium dynamics, which we will also get to see later. Okay, so you've seen this simulation, and you'll see significantly more of it. I won't be doing too much of the simulation in this particular lecture, but we'll come back to each of the examples I do in this lecture and spend a bit more time of it in the next video to describe the various properties of refractory period and other aspects of Hodgkin-Huxley type channel function. So let's start with the refractory period. So this is one of the classic observations in the behavior of voltage-gated ion channels, and indeed in the behavior of cells, which is that if you give a cell a stimulus, so this is a current pulse, we're doing all of this in current clamp. When you give a cell a stimulus, it causes an action potential. Well and good, that's what a stimulus is supposed to do. If then you give it a follow-up stimulus at one of these times, this is an overlay of multiple simulations or multiple experiments. So let's suppose we start with a stimulus here, and you give your second stimulus over here after a long time, after of the order of 20 plus 15 or 20 milliseconds. Then you get a nice action potential. Supposing you gave your stimulus a couple of milliseconds earlier than that. well, after some hesitation, you still get an action potential. But if you give your second stimulus any earlier than that, all you get is a little bump. And earlier than that, of course, you get an even smaller bump. Now, you might argue that, no, this is simply a function of the slow recharging of the cell. And to some extent, it is that. But there's a even more fundamental aspect of cell properties, of sodium channel properties in particular, which causes this refractory period. And that is the H gate, the inactivation gate, which we've already discussed in the class and in tutorials for a little bit. Let me spend a little time on this, because the H gate, or the inactivation process, is extremely important for the functioning of ion channels. So let's start with actually ignoring the sodium channel altogether. We'll ignore M and we'll ignore H. We will just look at N, which is the gate for the potassium channel. And potassium channel, as you recall, is nice and straightforward. It has only N to the power of 4. It does not have any inactivation process. So what do you get with N? That's the blue curve here. So N starts out at a low but not zero value. It's about 0.3. This is means that the channel is already somewhat open even at resting potential. Yeah. So it sticks around at 0.3. And then once you apply a current pulse, which isn't visible here, but the current pulse, if you recall, starts at 5 milliseconds and lasts for 1 millisecond. So when you apply the current pulse, the sodium channel does its thing, the cell depolarizes, and then the N gate starts to climb. The fraction in the open state starts to climb. It reaches about 0.8, and then it starts to go down again. Okay, now this thing is going down relatively smoothly. You can see that it's pretty much closed by around this 20 millisecond point, and that's when the second pulse comes in, let's say in the long interval case, in this case. And what happens? It happens very much the same as the first time round. The sodium channel causes a depolarization, action potential happens, and then the N gate opens and it comes down again. If you had the second action potential a little bit earlier, you'd have that curve. And if you had it a little bit earlier than that, well, you don't see anything very much at all happening with the N gate. Why? Because the cell never depolarized very much. You never got very far above resting potential, and so the potassium channel doesn't open. So this is what the N gate does. And just to remind you, G is equal to G max into N to the power of 4 for the potassium channel. Okay, so that's sort of the warm-up exercise. Now let's get to the main course, the functioning of the sodium channel. So in a manner very analogous to the N gate, but somewhat faster, you'll see that the M gate opens. This is the black curve. It starts out at a very low level. It opens almost to 100% open, and then it closes again. You apply the second pulse, it opens again. You apply the second pulse a bit earlier, it opens again. And you apply it a little bit earlier than that, it doesn't open, and we're about to see why it doesn't open. But at this point, there's nothing particularly exciting happening with the M gate either. The interesting stuff is happening with our friend the H gate, which is in red over here. So first thing to note is that H starts out at a fairly high but not anywhere near 1. It's at 0.6. If it were just the H gate present, then 60% of the channel would be available to open. Now, of course, it's not just the H gate. The M gate is also there, and M is close to 0. So you have to multiply those times N to the power of 3. So the channel is not at all open. But even if you were to completely open up the M gate, you would still only get 60% of the channel to open, because the H gate is very, very close to 60% over here. The channel, therefore, is in the closed state. About 60% of this channel is ready to open should the M gate magically go to 1, which it very nearly does. M gate goes to 1, the H gate starts to close, and it closes, and by the time we're over about here, something like 15 or 20% only of the channel is now available to open. The rest has become inactivated. This is the inactivation gate. When it shuts down, when it approaches 0, that means that the channel, no matter what the M gate is doing, the channel has to close. Just to remind you, G is equal to G max into M to the power of 3 into H. And so H is close to 0, therefore the channel is closed. G is close to 0. All right, so it dips down over here, the membrane potential note comes back down, and so the H gate starts to climb back up towards its resting potential value. And if you wait long enough, it's pretty much back there, and so the next current pulse, this one over here, is enough to trigger it to open. So you get the sodium channel. This is at 60%, so fine, that's enough to boost the system along. A little bit earlier, the climb is still almost done, and so you get another action potential. A little bit earlier than that, though, and now you're starting to get a little bit below your 60%. And it turns out that in this range, when you're below this, you don't have enough channels available. 60% is not enough. In fact, it's not even 60%, it's closer to 50%. That's not enough for the feedback process that's needed for the action potential, and so you fail to get the runaway buildup of potential, which is part of the action potential. So if you were any earlier than that, of course, you'd have absolutely no chance of the action potential, because n is very close to 0. It's a small fraction of 1. Okay, now you might ask, what happens if you give a stronger input pulse? Would you overcome this depletion of the open possibility of the channel? And indeed, that really happens. Yeah, so you can give a larger pulse. So here's the original pulse we saw earlier, and now we give larger pulses, and now you can see that a little bit earlier on the third one from the end, you got an action potential, but you still didn't get one over here. Yeah, so this is a relative refractory period, which means that as you boost up the strength of the second stimulus, you will be able to push the channel into the open state, even though H is somewhat depleted, because you've pushed it a bit harder. So now the sodium channel, the M gate, is pushed enough that it can start to have its feedback process. So that's relative refractory period. But you can, at some point, you're going to get to this state where even if you give an absolutely monstrous second pulse, yeah, which you can see here, so you were able to get the last 4 you were able to get, but if you get any closer to the first pulse, it doesn't make it. It doesn't have enough feedback for the channel to give an action potential. Okay, and again, you can see that through here, right? If you get closer and closer to the first action potential, the fraction of the channel available to participate in opening is now of the order of 30%, or even 20%, or even 10%, right? With so little channel available, you just cannot have the runaway feedback. The current going through the sodium channel, the little available amount of sodium channel, the 10% available, is not enough to charge up the capacitor fast enough to get a buildup. So that's the absolute refractory period. And the key thing to note is the process of inactivation. If the channel has recently been opened, the H gate is depleted, it's close to 0, and then you don't have enough channel available to open anymore for the next action potential. And this gives rise to refractory period. But there are many interesting things that also come around as a result of the behavior of inactivation, and we'll see some of those. Okay, so we'll run through all of these things. We'll have a good session with demos to see how these things work in more detail. Here is a very interesting example of what happens due to the inactivation gate. And it is this, that the threshold for firing an action potential is a function of the history of the channel. In other words, it's a function of what were the potentials that the channel received at earlier times. And it goes like this. Supposing I give an injection current which is negative in sign. So what do you expect happens? Well, the cell becomes more and more hyperpolarized. Okay, so far so good. This is what it would do if it were a passive neuron. Now I release the hyperpolarization, I release the current, it goes back to 0. The cell charges up, but it doesn't stop there. It doesn't stop at resting potential. It keeps going, and in fact, it produces an action potential. How can this be? Well, here's a hint. The answer to many of these puzzling behaviors is sodium channel inactivation. And indeed, that is what is happening here. Yeah? So here we're going to the dreaded H gate opening and closing function. And what we see is that this is the H gate in red, remember? As the cell goes more negative, the H gate becomes larger. The H fraction approaches 1. It gets about 80% open over here. Yeah? And so that is enough that when you release the the inhibition, when you release the negative going current, there's enough sodium channel that just crossing resting potential is enough to have the runaway feedback process. Okay, so the converse is also true, that if you have been holding the cell a little bit positive for a while, the H gate will become more negative, will become smaller, and it will be harder to get an action potential. So you are, in effect, you are modulating the threshold by the past history of the ion channel. If the past history was more positive, then the H gate would have gone down and your threshold would be higher. In this case, we have the history is that the cell was more negative, about minus 20 millivolts below resting potential. The H gate became more open, and then the threshold effectively is resting potential itself, and you get an action potential without any further activity. So this is called rebound for obvious reasons. You've gone down and you release the negative and you rebound and you get an action potential. So this is a rebound action potential, and it's another illustration of some of the fun things that can happen due to sodium channel inactivation. All right, so now let's move on to what the squid axon was actually designed for, designed through evolution, really. Its job in the squid is to propagate signals as fast as possible from the point of stimulus to the muscles so that the squid can escape. And that is what the squid giant axon is designed to do. That's why its diameter is so large. It's because it has to propagate the signal very, very fast. It's part of the escape response. All right, so you've already seen this. This is what it looks like if you just record from a small membrane, a single compartment, which is what Hodgkin and Huxley did. You get an action potential in one place. Now, on top of this, let's add the following property, which you already know well, which is that if you have a long cable, no longer this short single compartment thing, but if you have a long cable, then if you recall, if you get a depolarization, there will be a passive propagation of the signal along the length of the axon. And you remember this, it's got an exponential decay if you wait long enough, but we're not waiting here. What's happening is that you get the passive propagation, and that means that now the potential from this compartment has propagated into this compartment, causing the opening of ion channels, and sure enough, you get an action potential there. So this is a very, very cartoonized version of it from Alberts et al. And this is how you can think about it. So they have all these pretty schematics. That's the closed sodium channel. That funny looking thing is the inactive sodium channel. And this one with a hole in there is the open sodium channel. Okay, and the direction of propagation of signal is along this way. And this is how it goes. Let's start at the open place. Yeah, so here the channel is wide open. Sodium ions are rushing in. The cell is becoming more positive. Because it's more positive, current flows that way and it flows that way. Yeah, this is where the action potential was a little while ago. Current flows this way, but it can't do anything. Why? Because the sodium channels are all inactive. They are not going to open. They're in their absolute refractory period. So all of these sodium channels are closed, and it doesn't matter that current tries to flow this way. They are not going to open. However, on the forward going side of the action potential, your current goes this way, the positive charge flows this way, and that depolarizes the membrane over here, and it causes the closed channels to start to open, right? And so a little bit later, you take another snapshot of it, and it's very much the same, except that now these channels over here, which had been depolarized, they are open. The channels over here, which had been open, are now inactive, and the system propagates merrily along. So there's some interesting things which you should bear in mind as intuitions about how the action potential propagation happens. First of all, it's actually quite slow compared to passive spread of signal. This may seem surprising to you, but just remember that passive propagation just involves equilibration of charge along the length of a conductor. It does not need to wait for your various ion channels to open and close. So this is actually fast. Another way of thinking of it is that you have to have the passive propagation before the channels can open. So the actual opening of the ion channels is somewhat slower than passive spread, and that is part of what determines the rate of propagation of an action potential. It's not just a passive property, it's also a property of the speed of the ion channels. Another key thing, of course, is that it is self-sustaining. That is, that you trigger an action potential here, and the energy for it to propagate, if you recall, is in the already present ion gradients. And so it will sustain itself. It will open the new channels a little bit further down. They will become inactive. It will keep propagating because there's a stock, so to speak, of closed ion channels which can be opened before they eventually become inactive. And the energy for that is coming from the ion gradient, which has been set up by the ATP pump for sodium and potassium. The action potential is all or nothing. This is simply another way of saying that there's a threshold. If you cross that threshold, you get the spike. If you do not cross the threshold, it sort of fizzles out. How can you make it faster? Well, you need both things. You need to have passive spread, which is more effective, and there are multiple ways to do this. We'll see a bit more of that. Another way to make it faster is to have a very high channel density, which means that the currents that pass are much larger, which means that larger current means that they can propagate a greater distance, that the capacitances and resistances that cross the membrane don't remove so much of the current. So all of these things help to increase the speed. We'll see later even more clever ways to increase the speed of propagation. And here it is. If you really want to have very fast action potential propagation, this is a trick that our vertebrate ancestors came up with. Invertebrates do not have this. It allows you to go from this monstrous 500 micron diameter axon to axons which are 10 microns or even smaller in diameter, and yet conduct signals many, many times faster. And it is through myelination. And basically what myelin can be thought of is like it's insulating tape wrapped around the, so this is the insulating tape wrapped around the axon, and that, if we'll go through the argument, that in itself vastly increases the electrotonic, the lambda, the length constant. But even so, there is going to be a decline with distance, and then you have little amplifier junctions which are called nodes of Ranvier, at which there's a huge density of the sodium and potassium channels to boost the action potential so that it can make a jump to the next location. And in a moment, I'll show you simulations of this. So just to remind you, here's the squid giant axon, roughly 500 microns across. All its regular axons are much, much, much smaller, as you can see. Yeah, this is huge. And the vertebrate, the frog, the human axon is much smaller, and it is much more effective, right? So here we go. Squid, you can achieve 25 meters a second, which is not too bad at all. The frog can achieve the same thing. Here's the difference, though. This is done with a 500 micron axon, incredibly huge metabolic load. This is done with a 12 micron axon. The cross-section area is that much, quarter of a square millimeter. Here it is much, much, much smaller because, of course, it is proportional to the square of that. Here, the energy consumption is 5,000 times that, simply to keep all of those ions, all of the metabolism going for this vast, gigantic axonal fiber. So this is a huge innovation, shall we say, that our very, very distant ancestors came up with to have more efficient signal propagation. In humans, you can have, I believe, the fastest action propagation is of the order of 100 meters a second, which is pretty jolly good. All right, so I'm just going to show you a couple of cool simulations of action potential propagation, just so that you get a sense of how they work. Okay, so here we go. Here is axon. There's the soma. That's where we're applying the stimulus. It's in a spiral so that you can get a larger range of length inside this field of view. I'm going to zoom in a little bit. And what you can see, the bright colored propagating traveling wave is the action potential. And it goes around. You can see these are the little compartments in the simulation. You can see the action potential going along. If you look closely, you'll see that the tail of it is actually extra hyperpolarized. It's darker than the rest of it. Let's just run it a little bit more. There's another one, action potential, bright, and now it becomes very, very hyperpolarized. The signal is propagating merrily along. and this is how an action potential works. And this is what you would get if you were simply to record from the soma. You'd get a couple of action potentials. But that's what it looks like as it propagates along. What I'll do next is I'll show you what happens with myelination. So just hold on a second. Here we go. Here we have a myelinated axon. Very quickly, to show you, here is one node of Ranvier. Here is another one. There's another one, and there's another one. We depolarize the cell. The action potential starts, and now it's propagating passively all the way along. The passive signal reaches the node of Ranvier, and then bingo, it fires. And very rapidly it propagates to the next junction, that fires. And very rapidly it propagates there, and it fires. And it propagates there, and it fires. It's sort of leaping from one node to the next. There we go again. It's depolarized, and in this case it wasn't sufficiently large to cause this to happen because of sodium channel inactivation. We'll have to wait for another action potential. There goes the soma. Now it's depolarized the axon, and is it going to cause this to fire an action potential? Yes, it fired an action potential. The signal propagates passively very fast. It reaches there. It propagates passively very fast. It reaches there, and it propagates, and it reaches there, and bingo, you get another action potential. So you really have to see just how fast the signal propagates passively, and then it spreads in both directions. Now this simulation is a little bit at the edge. The channel density that I've used and the internode distance is somewhat more than you have in real cells. So that's why you had this funny situation where one of the action potentials over here in blue, one of the action potentials failed to get a propagating signal. So the soma went like that, 3 action potentials, in fact 4 when we weren't looking, but the propagation only happened in 2 cases. After skipping one there, it propagated after that, and this one didn't have time to propagate. So here you've seen a couple of aspects of action potential propagation. One of them is the jumping, the saltatory conduction, which is what allows you to jump from the first place to the next node of Ranvier, to the next node of Ranvier, and so on. And you also saw that if the signal is not strong enough to trigger the action potential at the node of Ranvier, you get what is called a failure. So let's get back to the lecture. So you saw this simulation of propagation of action potentials in normal squid type axons and in myelinated axons. So why is myelination so good? Just to recall, the length constant is square root of resistivity per unit length, Rm divided by per unit length Ra. Now what happens when you myelinate? What happens if you put insulating tape around it? That's what these red zones indicate. So Ra is not going to be affected. You're putting insulation tape on the outside, it's not going to affect the internal conductance. So Ra is the same. Rm is the membrane resistance that is increased. It becomes much larger. Yeah? You put in many, many layers of myelination, so it can become 10 times, 100 times larger. What happens to lambda? So if it's square root of Rm by Ra, this is the same, this has gone up, and therefore lambda grows as the square root of Rm. And so the passive propagation is better. Yeah? There's also another bonus, which is also due to the myelination, which is that because you have multiple layers of insulation, it's as if the gap between the conductors is larger, and therefore capacitance gets smaller. And so as a result of this, your charge that needs to charge up the membrane is also smaller, and that also speeds up propagation. Of course, when you have the smaller diameter, metabolism cost is lower. Further, it's lower because you don't have to put ion channels all along, you only have to put them here. The counter to that is that now you also have to power up the cells, the oligodendrocytes that provide the insulation around the axon. So these are all the pluses and minuses of myelination. It's certainly far more complicated for the cell to organize, but it is very, very efficient, it's faster, and it causes much less metabolic load. We also saw this case of amplification of failure. So here's your starting action potential. Let's suppose that this is the threshold for the next one. If your decay was sufficient sufficiently minimal such that the next location was above threshold, you could get amplification by having an action potential there. If, however, the decay took it below the threshold, you would just end up without any further action potentials. In other words, you would have a failure. Now, you saw an example of failure that was kind of a sort of synthetic case, but there's actually a physiological case which is somewhat more prone to failure, and it is this. If you have an action potential coming along, jumping from one node to the next node to the next node, what happens if it comes to a branching node? Well, what happens here is that here you have a kind of a double load. You have both you have the load of that as well as that myelinated segment. And it so turns out that in many cases where there is failure, it happens to be somewhat closer to a branch point than it is along the length of an axon. In fact, there are certain diseases which cause failure of such propagation. So you can even have weird cases where the propagation is successful along one branch and fails along the other branch, right? But the key thing to remember is that almost always there is a very, very high what they call safety factor. That means that the decay of the signal as it propagates is much, much smaller than is needed to cross the threshold for the action potential. So you're really very, very safe. There's a huge safety margin built into almost all natural healthy axons. It's usually in unhealthy cases where you might end up with failure of propagation. All right, so let's move on a bit. Hodgkin-Huxley, even though they were way, way ahead of their time, they of course did not know everything. The simple form that I've discussed with you, going from closed to open to inactive, which I already said is an approximation, is even more so now known to be an approximation because you can think of multiple closed and open states, and for the matter, multiple inactive states. So you have closed one, closed two, open, inact, and all of these can have rate constants between these chemical conversion steps, and all of those rate constants can be voltage dependent. You can see how messy this is getting. Yeah? And this is actually a simple diagram of this kind. They're models of Hodgkin-Huxley kinetics or post-Hodgkin-Huxley kinetics, which have many, many closed and open states. These are really, really nasty to characterize. They give a somewhat better approximation to the behavior of the channels, which is relevant in some cases, but in the vast majority of models and physiological contexts, Hodgkin-Huxley kinetics is sufficient. So just to remind you, these are the Hodgkin-Huxley kinetics. The conductance is the maximal conductance times m to, in this case, power of 3 times h to the power of 1. For the potassium channel, it is simply n to the power of 4. M and h are the fractions in the open state. There is a closed to open conversion and back again with a certain rate constant. The rate constants are a function of voltage, and the equivalent, they can be derived from the approach of m at a steady state value, how much is the fraction open at a steady state value, and they also need information about the time course of opening and closing. So this is a relation that you can kind of use to estimate the mapping between alpha, beta, and tau and m infinity. So here it is, closed to open, alpha, beta. In steady state, the ratio of open to closed is simply alpha over beta. Okay? Therefore, fraction open, which is open divided by total, is equal to m. That's by definition. That's the definition of m. In steady state, at time equals infinity, we have open by closed is alpha by beta. Therefore, open by total, which is that, is alpha by alpha plus beta. Okay? You can work through the algebra, but it's very simple algebra. And further, you can show by solving the charging and the opening and closing exponential form that tau is simply 1 over alpha plus beta. So this is the mapping between m infinity and alpha and beta, and tau and alpha and beta. So as I said, they can be derived from each other. It's easier to experimentally measure m infinity and tau, but in terms of calculating it, it's easier to think of alpha and beta. Okay, so we just to summarize, we looked at sodium channel inactivation. We saw some examples of refractory periods, and we'll have a demo of this. We saw examples of rebound. We'll have a demo of this. And we saw some demos of action potential propagation through the squid type axon and through a myelinated axon. And just because I'm sure you want to do this, here is the assignment for the week. Think about the current voltage curves and draw them for each of these cases. We've actually done this in one of the tutorials. And second, think about a cell with a certain length. Think about what happens if you have voltage clamp in a cell which is not a small cell. In a long cell, what happens if you voltage clamp one end? You've done enough passive cable theory to see what happens over here. And finally, number 3, if you want to do it, try this one as well. See what happens if you have a channel that is in this long cell that is closed and opens if the potential crosses this. So just work through it. Enjoy.